Okay, so as usual, don't forget the seating survey. Deadlines this week. Thursday, the small group activity will be due at 5 p.m. Friday is the Newton homework. Next week is going to be exam number 3, which will be covering acid-base equilibria and up through today's material. There will be no new content introduced next week, so we will be spending the class days next week doing review and sample test type questions, those sorts of things. This week, I again do not have content videos up. I'm hopeful that over Thanksgiving break, I'll be able to catch up on that, and we'll be able to go back to normal following Thanksgiving break. But what this means for this week is that yesterday and today are identical introductions to this week's material. And then Wednesday and Thursday will be Q&A, muddiest points, those sorts of things. So if you happened to see yesterday's class, there's not going to be anything new today. And I guess that's it on that. So do we have any logistical questions before we get started on some content? Okay, let's get going. So we have one major topic for today, buffers. I'm sorry, we did buffers, titrations. And then following that, we're going to talk briefly about a couple of other equilibria concepts, including coupled equilibria and solubility products in particular. But titrations are really the big topic for today, because in the other material, the other topics, there isn't anything really new other than a couple of definitions. It's just that these are some extra examples of some of the equilibrium stuff we've been talking about so far. So let's talk about titrations. And I want to start by giving you sort of an overview of what a titration experiment looks like. So generally what we do is that we have a solution that we are analyzing, and we have above it a burette, which allows us to add controllable amounts of another liquid to the stirred liquid that is in the beaker in this case. A burette has a stopcock on the bottom that we can turn to one position to allow flow to go through, or we can turn it to close. And we have enough control over it typically that if we are careful about how we twist it, we can release one drop at a time very effectively. And in some cases, we can even get a partial drop. So a small amount will then hang off of the bottom, which we can then touch to the side of the beaker to get it to drop in. And then the burette itself has these graduations on it that are extremely precisely and finely divided so that you can measure extremely accurately the amount of liquid that you have added. Simultaneously, we have some mechanism for monitoring the solution the solution mixture that is in this case, beaker. This particular setup is shown using a pH meter. So you would add a certain amount of the liquid that is in the burette to the beaker. You would then allow it to equilibrate. This is sitting on a stir plate right now so that it's being mixed constantly. You let the pH equilibrate and you read off a pH value. You then add another amount of the liquid to the beaker, you'll get a different value, and you keep doing that. Titrations don't necessarily have to use a pH meter. If it is common to use a chemical indicator that will change color under certain conditions, and we'll get to that in a little bit. We're going to start by thinking about monitoring the pH using a pH meter, however. So any questions about the experimental setup, how this is working? We'll get into why we want to do this in a little bit once you see some of the characteristics of what the titration looks like. Okay, so what we are going to do is start with the simplest type of titration, which is a strong acid, strong base titration. And so we are going to start with, in our beaker, 25 mils of 0.100 molar HCl, and in our burette, we are going to have 0.100 molar sodium hydroxide that we can then control how much of that we are adding. So you should recognize this as being a neutralization reaction that is happening, strong acid plus strong base. And what we are going to do is look at what the pH is going to do of the mixture down in the beaker as we add different amounts of the sodium hydroxide to it. Now, in this case, I have picked the two concentrations here to be identical to make the math easier. They do not have to be identical. You just have to take into account how they are different if you choose different values. So the cases we're going to look at are going to be no sodium hydroxide added, half as much sodium hydroxide as hydrochloric acid added, an equal amount of sodium hydroxide added as the hydrochloric acid, and then half again as much sodium hydroxide added as hydrochloric acid. And so this is going to take us through the different regimes of pH that we're going to be looking at. So for the first data point where no sodium hydroxide is added, this calculation of our pH is extremely straightforward because we're just dealing with 0.1 molar HCl, and that's all it is. So that means that our concentration of the hydronium ion itself, because hydrochloric acid is a strong acid, is 0.1 molar. We know that pH is the negative log base 10 of the hydronium ion concentration. So our pH in this case is going to be 1. So that one's relatively straightforward. Case B, where we are adding half as much sodium hydroxide as HCl. So thinking about this, that means that half of the sodium hydroxide, all of the sodium hydroxide is going to react with half of the HCl. So the neutralization reaction is H3O plus aqueous plus OH minus aqueous yields 2H2O liquids. And if we have twice as much hydronium as we do hydroxide, then once this reaction goes, we are simply left with half as much hydronium as we started with. Now, the complicating factor is that by adding the sodium hydroxide, we have changed the volume, so there's a dilution effect we have to deal with as well. The way we do that is by calculating the number of moles that we are dealing with, and then dividing that by the volume that we have at that point. So how much HCl did we start with? So we have 25 milliliters times our concentration, 0.100 mole of the H3O plus over 1 liter of the H3O plus. In order to have milliliters and liters cancel, we need to do our dimensional analysis. 1 liter is 1,000 milliliters. And so this will tell us how many moles of hydronium we started with. So 25 times 0.1 gives us 2.5. divided by 1,000 makes it 2.5 times 10 to the minus 3 moles of hydronium. Now, the argument we just went through said that half of this reacts away in this case because we added half this amount of the hydroxide. So we divide this by 2 to find out how much hydronium there is left after the reaction. So we have 1.25 times 10 to the minus 3 moles of hydronium after the neutralization reaction has happened. We want this to be a concentration, so we are going to divide by our volume, which at this point now is going to be 25 milliliters plus 12.5 milliliters, or 37.5 milliliters. 37.5 milliliters is 0.0375 liters. And so this gives us our hydronium ion concentration. So 1.25 times 10 to the negative 3 divided by 0.0375 gives us 3.33 times 10 to the minus 2 molar. And this is, remember, this is our H3O plus concentration. pH is, as we set up here, negative log base 10 of the hydronium ion concentration. So our pH is now 1.48. Okay. So we have handled our first case where we didn't have any hydroxide added. Our second case where we added half as much sodium hydroxide as the hydronium we started with. Our next case is quite simple. Our next case, C, where we have an equal amount of sodium hydroxide as hydrochloric acid, means that they react away completely, leaving us with neutral water, and so our pH equals 7. Okay. Case D, the best way to start with this is to think about starting at the position of pH 7, starting at the case of C. And so what we are doing then is we are adding an extra 12.50 milliliters of the sodium hydroxide solution. And so that is what is going to determine our concentration of hydroxide. That's the extra hydroxide that's left over. So we need to convert this to moles and put it over our new volume. So we 12.5 milliliters of the sodium hydroxide solution, 0.100 moles of sodium hydroxide over 1 liter sodium hydroxide times, we need our milliliters and liters to cancel, so 1,000 milliliters of the sodium hydroxide in the denominator, 1 liter of the sodium hydroxide in the numerator, and conveniently, no, that's all right. We'll go ahead and do it this way. So this is the 12.5 times 0.1 takes us to 1.25, divided by 1,000 gives us 1.25 times 10 to the minus 3 moles of hydroxide. We can get our pOH from this by taking the negative log base 10 of that value. Oh, I'm sorry, that's moles. We can't, we have to divide this by our volume. So taking this value and putting it over our total volume, which is now going to be 25 plus 37.5, which is 62.5 milliliters, so 0.0625 liters. Now we get our concentration. So 1.25 times 10 to the negative 3 divided by 0.0625 gives us 0.02 molar in hydroxide. And so our pOH is going to be the negative log base 10 of that, or 1.70. pH is 14 minus the pOH, so that's going to be 12.30. Okay. Before I start to take these 4 results and put them into context, are there any questions about these calculations that we just did? These should have looked relatively straightforward to you because we're not even dealing with an equilibrium situation at this point. This is just about recognizing a neutralization reaction. Pardon me. My allergies are acting up. So it's just dealing with dilutions, and it's dealing with a neutralization reaction. Okay, so let's put this into context. There's nothing particularly magical about these particular 4 values that I picked here. I picked them because they are in different regimes. In the first case, we're looking at a still acidic solution, and so we have what we are doing is figuring out how much of the acid has been reacted away and looking at the leftover. Here in the case C, we recognize that we've reached the equivalence point, and where there's the same amount of hydroxide and hydrochloric acid, so we can immediately write down that that the pH is 0. And in the last case, we had to go through the hydroxide because there was more hydroxide than the hydronium. So that's why I picked those particular values to look at. But we could have picked any values we wanted. And this is a plot that shows what the titration curve ends up looking like if you pick a bunch of values. So I put this together in Excel. And what you see here is that as the pH changes relatively slowly, I mean, it does change, but it changes relatively slowly until you get close to the equivalence point. Equivalence point here, we have pH equals 7. We have, it's happening at 25 milliliters of added NaOH. And right around that point, the pH is changing very dramatically, very, very quickly. And then once it's done changing, you end up with a flattening out again. This is the general shape of a strong acid, strong base titration curve. So what we're going to do now is look at the next most complicated example with a weak acid being titrated with a strong base, and we're going to see how this changes because there's a lot of information about the weak acid that we can get from this kind of titration. So we're going to do pretty much the same experiment that we had here, but we're going to be using a weak acid. In particular, instead of HCl, we're going to do acetic acid, CH3COOH, but I'm going to abbreviate it as HA, as we very often do. In order to do this, we need to know the equilibrium constant for this weak acid. And so we have a pKa for acetic acid of 4.76. And so our Ka is going to be (10 to the negative 4.76, which equals, let's do here, 4.76, change sign, 10 to the x, and we get 1.74 times 10 to the negative 5th. Okay, so that's the information we're going to use. We are going to now use exactly the same 4 test cases to figure out what we're looking at, figure out what these do. Question on chat, did I say this is a weak acid, strong base? Yes, weak acid, strong base. Oh, it's off the top, that's why you can't see it. Let me back it up. There we go. Yes, weak acid, strong base. Acetic acid is the acid we're looking at. So let's take a look at our first case here of no sodium hydroxide having been added at all. In this case, we have our ice table. Let us write out the expression, the standard acid reaction, which is you take your acid, you react it with water to form A minus aqueous liquid plus H3O plus aqueous. We are starting off with, we are told, 0.1 molar of the HA. We'll start off with 0 of these, minus X, 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 0.1 minus X, X, X. Let us try to make the math simple, and we'll double check it by neglecting this X value right here. We write down our expression for the Ka, and remembering that we know that the Ka is 1.74 times 10 to the minus 5. Our expression is A minus H3O plus over HA. This is going to be X squared over 0.1. So looking at the far left and the far right, multiply through by 0.1. So we have X squared equals 1.74 times 10 to the minus 6th. And if we are tracking units, that's molar, this is molar, so we end up with molar squared. Take the square root of both sides to find X to be 1.74 times 10 to the negative 6th. Take the square root, and we get 1.32 times 10 to the minus 3 molar. And that is our hydronium ion concentration. So we double check, is this in fact small compared to the 0.1 we started with? Yes, it is. So we're okay in doing that approximation. So we now find our pH to be the negative log base 10 of that. Our pH is 2.88. Okay. How did I get the negative 6? This negative 6 here? What I did was I took the Ka value of 1.74 times 10 to the negative 5, and I multiplied both sides by 0.1. So that I got rid of the 0.1 on this side, and so that simply moves the decimal point over by one value here. Okay, so we now have solved A for the for this case. Let's take a look at B. B is a case where we start with the same amount of HA, but we now add half as much sodium hydroxide. The way to think about this step is that the hydroxide, as a strong base, is going to pull off a proton from the HA. So that means that however much base we have, however much acid we have, the HA, half of it is going to stay as the acid, the other half is going to get converted into the A minus. So let's figure out how much we have. We have 25 milliliters with a concentration of 0.100 mole of the HA over 1 liter of the HA. 1 liter is 1,000 milliliters. And so this is the same set of numbers we used before. So this becomes 2.5 times 10 to the minus 3 moles of HA that we started with. So what this means is that after the initial neutralization step, we should have concentration of HA equals half of this at 1.25 times 10 to the minus 3 moles HA. And the other half has been converted to the A minus of 1.25 times 10 to the minus 3. Notice that what we have here is half, an equal amount of the acid and its weak base, its conjugate base. I didn't put this over their volumes, so I did make a mistake here. So this needs to be, each of these need to be over our volume of 37.5 milliliters. So divided by, here, we'll do these. 1.25 times 10 to the minus 3 moles over 0.0375 liters to give us 1.25 times 10 to the minus 3 divided by 0.0375 gives us 3.33 times 10 to the minus 2 molar in each of HA and A minus. Now, because we are in the buffer region, because we have equal amounts of the weak acid and its conjugate base, the easiest thing to do is to use the Henderson-Hasselbalch equation. pH equals pKa plus log base 10 concentration of A minus over concentration of HA. Well, concentration of A minus and HA are the same, which means that the ratio is 1. The log of 1 is 0, and so the pH equals the pKa, which we had as 4.76. Okay. So let's now take a look at C. In case C, we have an equal amount of strong base as we do of the weak acid. So if we think about what's happening for this, and if we think about the strong base as pulling off the proton from the weak acid, all of the weak acid will have been converted to the conjugate base. So for this calculation, we have to use the base reaction for the conjugate base. So A minus aqueous plus H2O is in equilibrium with HA aqueous plus OH minus aqueous. So the first thing we need to do is to find out what our concentration of A minus is. Well, we've already calculated how much HA we started with, which was, I'm looking for it here, which was this value right here, that many moles. So let's take our 2.5 times 10 to the minus 3 moles of A minus, since it's all been converted into A minus, over our volume in this case, which is 25 mils plus 25 mils, or 50 mils, 0.05 liters, gives us hello, there we go, 2.5 times 10 to the negative 3 divided by 0.05. That doesn't seem right, does it? 2.5 times 10 to the negative 3 divided by 0.05. Nope, I guess it is right. Gives us a 0.05 molar concentration of A minus. And actually, if we think about this, that makes sense because we started at 0.1 molar and we have now doubled the volume. We should be at 0.05 molar. So I shouldn't have been surprised by that. So 0.05, 0, 0, minus x, 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 0.05 minus x, x, x. Let's try neglecting this and we'll see if it works or not. And so we need our KB to be x squared over 0.05. But now, what is our KB? Well, we have the Ka is equal to 1.74 times 10 to the negative 5 molar. And the conjugate basis Kb is related to the Ka by Ka times Kb equals Kw. So, and remember Kw at room temperature is 10 to the negative 14 molar squared. So our Kb is Kw over Ka, 10 to the negative 14 molar squared over 1.74 times 10 to the negative 5 molar. To the negative 14 divided by 1.74 times 10 to the negative 5 gives us 5.75 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molar. So we put that over here, 5.75 times 10 to the negative 10 molar, and we solve for x. So we take this value times 0.05, and we get x squared equals, remember that should be a molar, 2.87 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 molar squared. And so we take the square root of that to get x of 5.36 times 10 to the negative 1, 2, 3, 4, 5, 6 molar. That is our hydroxide ion concentration. So our POH equals negative log base 10 of that, 5.27. And so our pH is 14 minus this, 8.73. Okay. The final point that we want to do, part D, we are adding in sodium hydroxide to a system that we have now essentially, at this point, we will have flooded it with base. And so what we simply do here is identify how much hydroxide is past the equivalence point. All of that's going to be hydroxide. And so we then just determine the pH from that, which is identical to what we did in the first, for the strong acid, strong base case. And so our answer is going to be identical because the procedure is going to be identical. And so we will end up with a pH of 12.3 for that particular value. Okay, so the important points here are that we are, when we have a weak acid, or if we're doing a weak base, you have to identify, are you in a regime where the equilibrium is playing a role? If you're past the equivalence point, then the pH, then the equilibrium is not really playing a role, so you treat it like strong acid, strong base case. If you are in a regime where you're not really in the buffer region, then you use an ICE table. That's what we did in A and C. If you are in the region where that's a buffer region, then the approximations that go into the Henderson-Hasselbalch equation are good for you. And so that's what we did for part B here. And that in that case, we were able to use the Henderson-Hasselbalch equation to more quickly get to our final values. You also, in this case, have to keep track of when you have performed the reaction, have you eliminated all of the acid you started with, meaning that you now need to be dealing with its conjugate base, which is what we had to do for step C. So those are the different regimes that we're talking about in this particular case. When you do this, so let me start by reminding you of what the strong acid, strong base one looked like. That didn't autofocus right, did it? There we go. So the strong acid, strong base case, we had pH of 7 at the equivalence point and a very sharp rise here. When we have a weak base being titrated by a weak acid titrated by a strong base, the volume for the equivalence point is still the same, because the equivalence point means that we have an equal amount of the acid and the base. But notice that our pH at that point has changed. It's here above 8, which is in fact what we calculated. And we see here that we initially have a rise of the pH, and then we enter the buffer region, where it's relatively flat for quite a while, and then it starts to go back up again. So this point here is known as the equivalence point. And because the pH is changing so dramatically at that point, you can determine the volume for that equivalence point extremely precisely, to within a fraction of a drop that you are adding. So you can find this position very, very precisely. Here at 12.5 is the half equivalence point. And that corresponds to the point where you have an equal amount of the acid and its conjugate base in solution, which means that you are squarely in the middle of the buffer region. Remember the Henderson-Hasselbalch equation, where pH equals pKa plus log base 10 of A minus over HA. Well, at the half equivalence point, A minus over HA is 1, the log of 1 is 0, and so the pH equals the pKa. So from this plot, we can very precisely determine the pKa of the weak acid. So notice what's happening here. So I pointed out that we can determine this volume really precisely because the pH is changing so dramatically right here. So we can get the volume really precisely. Take that, divide it in half, and you get something that has a very low slope, which means that you are now determining the pKa very precisely. So this titration curve is an amazingly powerful tool to measure an equilibrium constant for an acid-base reaction? Okay, so I know I have thrown a lot at you so far here with this. Let's see if there are any questions. There's several in the chat. Let's take a look at can't you do it the same way you did for strong acid, strong base? Confused on why you do a nice table. So in strong acid, strong base case, there's no equilibrium going on. So you have to use an ice table when you have an equilibrium that you're dealing with. How do you determine that equation? Which equation were we looking at for that question? Oh, switching to the base? Okay, so this is something that in going through the questions people are asking about the small group activity, there seems to be some confusion about what is meant by the standard acid reaction and what is meant by the standard base reaction. Take any acid, HA. Why are we calling this an acid? Well, because an acid is a proton donor, so I'm pointing out the proton that is on it. A is simply whatever it is that it's attached to. So you can represent any Bronsted-Lowry acid as HA. The standard acid reaction is that the HA reacts with water and it acts as an acid. What does an acid do? It donates a proton. So after HA has donated a proton, what's left is A minus. It has donated it to the water, so you have H3O plus. So you don't have to go around memorizing different acid reactions for different acids. They're all the same. The standard Bronsted-Lowry acid reaction is just this, okay? And so the Ka, which is the equilibrium constant for this reaction, is also always of the same form. A minus, H3O plus, over HA. That's it. That is all there is to a Bronsted-Lowry acid. Now, if we have reacted it away so that we only have the conjugate base left, then we have to think of it as a base. So what is the standard base reaction? Well, not even thinking about comparing it to this one just yet. A standard base reaction is you take base B, and just like we did for the acid reaction, you're reacting it with water. And that's in equilibrium with the products of it acting like a base. Well, what is a Bronsted-Lowry base? It's a proton acceptor. So you end up with BH plus aqueous. And after the water has lost a proton, you are left with OH minus aqueous. So again, for a base reaction, you don't have to memorize different base reactions for different bases because it's all the same thing. And you don't even need to memorize this one because if you think about what a base is, a proton acceptor, this just is the only thing you can write down for it. And again, the Kb for this is going to be the same, BH plus OH minus over B. But now let's compare these two. We said up here, if this is a weak acid, then this is its conjugate base. So let's now write the standard base reaction for A minus. A minus, aqueous. Our standard base reaction is reacting with water, liquid. It's acting as a base, so it is pulling a hydrogen off of the water. So you end up with HA, and you're left with OH minus from the water. So if you are dealing with a conjugate base, treat it like a base. Now, it's easy to look at this and say, oh, well, all you did here was you wrote the reverse of this top reaction. But that's not what we did, because this one has hydronium in it. This one does not have hydronium in it. This one has hydroxide in it. So that is why there is the relationship Ka times Kb equals Kw, because Kw tells you how to get between hydroxide and hydronium. Yes.
So when it comes to the titration, when you have more base like volume compared to the acid, is that when you use the standard base?
Right, so in the context of a titration, so for people in the chat, I'm going to repeat the question. What are the criteria for when you use the base reaction rather than the acid reaction? So it's essentially when you have run out of the acid, so that you have so the equivalence point and beyond is when you do that. Yes.
Well, I guess the question. So for the equivalence point, could you use both, like a regular or?
Not as easily, because at the equivalence point, because you know it's a weak acid, then even if you have mostly the base, that base is going to be acting basic. So if you make a solution of sodium acetate, where acetate is the conjugate base of acetic acid, you know that that is going to be a basic solution. And so you need to be talking about the hydroxide in that case. Okay, so continuing on down, so in the context of this question here, where we were doing C, I think it was, and I have too many pieces of paper. Here we go. So on C, for the weak acid case, what I did here was write the standard base reaction for the conjugate base of the weak acid we're dealing with, and then just treated it as a standard ice table. So that's where that equation came from. Since everything on the screen is in a double arrow, they are all weak acid, strong base. So when we write this, we are indicating that there's an equilibrium that is happening. And so, yes, we are treating it as an equilibrium. I'm not sure if that answered the question. Any further clarifying questions on what we've done so far with a titration of a weak acid and a strong base? Okay, so there are some powerful things that you can do with the titration in addition to determining the pKa very precisely. Suppose that you don't know the concentration of the acid in the solution that you're dealing with. So when you do a titration, assuming you do know the concentration of your base very precisely, you can identify the equivalence point extremely well. And at that point, you know that the number of moles of acid equals the number of moles of base. You know the volumes of both of them at that point. So this is a very, very precise way to determine the concentration of your unknown acid, because it shoots up so fast. You get a very precise determination of a constant. This is one of the best ways you have to determine the concentration of an unknown acid. You don't even need to know the concentration of that acid in order to determine the pKa. Think about that. We needed to know the volume that was the equivalence point, but we didn't need to know the concentration. You just take the half equilibrium, the half equivalence point, and the pH at that point is the pKa. So there's a lot going on in this that's really powerful. Let's see, there's something here. So the first problem what we did was a single arrow, and this is a double to clarify. So the first problem we did was strong acid, strong base, and we treat strong acid, strong base as not an equilibrium, as unidirectional. So, so yes, so when there is a double arrow, it is indeed indicating that you're dealing with a weak acid or base. Okay, so next thing I want to glance at is polyprotic acids. So this example right here is phosphoric acid. And this is indeed one of the buffer systems that is talked about in detail in the small group activity that you're working on right now. So what we have in this case is, if we look at it, we have 3 equivalence points corresponding to the 3 deprotonation steps. So phosphoric acid is H3O, H3PO4, which can lose a proton to make H2PO4 minus, which can lose a proton to make HPO42 minus, which can lose a proton to make PO43 minus. So phosphoric acid, dihydrogen phosphate, hydrogen phosphate, and phosphate. And so this equilibrium here is what's going on here. So we could buffer in this region between these two, and then we reach that first equivalence point here where you have completely removed the first proton. You can buffer between these two in this region, and then you can reach the second equivalence point when you have removed the second proton. You then can have a buffer region here, which is equilibrium between these two, and then you reach the third equivalence point and you have removed all 3 of the protons fully. Now you'll notice that the first 2 look like what we would expect from the previous titrations that we saw before. We have a very sharp rise that is happening in the sharp rise in the pH. But we don't really see that here in for the third one. The reason for that is that the Ka for this particular equilibrium is so high, the pKa is so high, that we're kind of running up against the limits of what we can see in water. There's nowhere really for the pH to go beyond this point. And so, we're not able to really see that sharp rise that you normally would in this case. But that doesn't matter for us because we can precisely identify the first equivalence point. This is going to be double that volume. This is going to be triple that volume. So you can find the equivalence point just from the first volume that you used without having to worry about actually seeing it experimentally as a rise. And again, you have the half midpoints, so the halfway point between these two, halfway point between these two. These are points where you have equal concentrations of the 2 species that are in the equilibrium that's mattering at that point. And the Henderson-Hasselbalch equation tells you that the pH at that point is going to be the pKa. So we have pKa 3 there, pKa 2 here, and pKa 1 there. Okay. Any questions on polyprotic acid titrations? Okay. Last part of titrations for now is to talk about indicators. So going back to this picture of what we're actually doing. Now, this can be kind of tedious to do because you're taking a lot of data points, you're having to really let it equilibrate. But if all you're trying to do is to find the equivalence point, if you don't need the pH at all the points in between, but if you just want the equivalence point, which is all you would need if your goal of the experiment is to find the concentration of the unknown acid you're dealing with, then all you really care about is when the pH has passed a threshold. You don't need to know the specific number, but you need to know when it's suddenly changing rapidly. And there are a bunch of compounds, So we have a list of compounds over here on the left. We have pH along the bottom, and you see these colored bars. Those are illustrating the color of the compound at different pH ranges. So one that I've used quite a bit down here is called phenolphthalein, and it is clear below pH of about 8, and at about 10, it's a pink or purple kind of color, and there's a transition from 8 to 9, from 8 to 10, where it goes from transparent to being brightly pink or purple. And so imagine that we are doing this titration and we are adding at a pretty fast clip the base, and our solution is beautifully clear. And then, we've got a stir bar going, so it's mixing pretty rapidly. And then we start to see the place where it's hitting, it starts to get pink. Okay, let's turn off the burette, and then the pink dissipates as everything gets fully mixed. Okay, at this point, let's start adding it in smaller amounts, slower. And then you'll see that the pink that hits is going to persist longer and longer before it dissipates away. And as that's happening, you slow down and you slow down even further until you get to the point where you add a drop and it stays pink. At that point, you've crossed that threshold and you now know you have reached your equivalence point, if you have picked the indicator appropriately. So here are two titration curves. This is a strong acid, strong base titration curve. This is a weak acid, weak base titration curve. And we have three different indicators on this. We have the phenolphthalein, which is right here. We have the litmus, which is in the blue, and we have methyl orange that is down here. Now, for the strong acid, strong base case, then all three of them would work relatively well, but the litmus would work really well because it's right there at the equivalence point region here in the middle. And you'd probably be off by maybe a drop if we did the methyl orange, maybe off by a drop in the phenolphthalein. But for the weak acid case, phenolphthalein will clearly work because it changes color right around the equivalence point. The litmus would be very bad because it's going to start changing color way down here in the buffer region. So picking the indicator that you use is very important in order to do one of these rapid titrations that you can do this way. Okay, let me glance over my notes. Did I forget any main topics for titration? So the last little detail on titration is I've been showing cases here of titrating an acid with a base. You can obviously do it the other way around. You could have the base be in the flask and you're adding controlled amounts of acid, and it would just be you're starting high and going low instead of the other way around. So there are no new concepts involved. You just have to keep track of, am I doing pH or am I doing pOH as you're going through the analysis. Okay. That's it on titration. Any questions on that before I move on to the little bit of extra equilibrium stuff? Okay, so there are two sections in the textbook that are actually going to be better for you than what I'm going to be talking about right now. And the reason is that these sections, that there isn't really any new material in what I'm about to present other than a couple of definitions. We're going to be talking about the solubility product, which we've already briefly introduced, and we're going to be talking about coupled equilibria. But what these two sections in the textbook do is go through a lot of real-world examples. And those examples are excellent. How do you use these ideas for water purification ideas? How do you use them for fluoride in drinking water? How do you use them just I think there are like 8 or 10 different examples that are real world that talk you through all of the details. So the two main topics we're looking at are the solubility product, KSP, and coupled equilibria. So let's think about KSP first. KSP is for an ionic compound that's a solid that can be in equilibrium with its ions in aqueous solution. Our KSP is just going to be the ions concentrations to their powers that you have. So picking an example, let's suppose we have aluminum sulfate. So this is a solid in equilibrium with aluminum 3+ and sulfate 2-. We have 2 of these, we have 3 of these, and so our KSP is going to be concentration of the Al 3+ squared times the concentration of the SO4 2- cubed. So no new concepts in what we're introducing here, but the terminology here of calling this a solubility product, well, because of what the dissolution reaction is, nothing on the reactant side shows up in the equilibrium constant. So what we have is a product, meaning multiplicative product of all of the ions. So that's why it has that term solubility product. And this is how you determine the solubility of substances in solution. And it's how you determine will something precipitate or not. So you check to see your concentrations, and if they give you concentrations that are higher when they multiply together than the KSP, it's going to precipitate out. That's really it. There's nothing more to solubility products than that idea. Last topic is coupled reactions, coupled equilibria. I think they may call them complex equilibria, which in the textbook, which simply means that there are multiple equilibria that are all active at the same time. And so here's an example, and this one also relates to the small group activity you're going to be working on because we are dealing with a carbonic acid buffer system. And so we have carbon dioxide in the gas in equilibrium with solvated carbon dioxide. Carbon dioxide in solution reacts with water to make carbonic acid. Carbonic acid can deprotonate once, it can deprotonate twice. And all of these equilibria are interacting with each other. The little bit of terminology that's introduced in this is something called the common ion effect. And the idea is that if you have multiple coupled equilibria, they're coupled by virtue of ions that are common among multiple reactions. So we have here the hydronium ion concentration, the H+, and so if we change, if one equilibrium shifts to change that H+, the other reaction will shift as well because of that change in H+. Or here we have bicarbonate in these two, and so if the top reaction shifts in a way to increase bicarbonate, then the bottom reaction will shift in response to that increase in bicarbonate. Okay. So one way to think about this kind of thing is to have your equilibrium in front of you and draw arrows based on Le Chatelier's principle. So let us suppose that we are looking at the increase, as something that causes an increase in the CO2 gas that we have. Well, that's going to shift the equilibrium this way by Le Chatelier, which means that the CO2 in aqueous solution is going to go up. Okay, now we need to go down here and say, okay, that's going to go up. which means that this equilibrium is going to shift this way, which means this is going to go up. Okay. Well, that is going to go up here, which means that the equilibrium is going to shift this way, which means that both this will go up and this will go up. So now we have this one going up, but then this one also going up. So it becomes a little less clear at this point which way this one is going to shift. And so at that point, we are trying to figure out what the effect of CO2 is. And the only place where we came to a point where we actually have to stop and think too hard about it is the last one. So we figured out a lot of things about what's going to happen in these reactions just by this goes up, so the reaction shifts this way, this goes up. Okay. So this idea of the common ion effect to track through complicated systems Le Chatelier's principle across, in this case, 4 different equilibria, which means 8 different reactions, can be quite powerful. Okay, and that is really all of the new material for this week, and in fact, all of the new material for this exam that's going to be coming up next week. Do we have any clarifying questions on anything we've gone over today? So the titrations are kind of the culmination of all of the acid-base stuff that we've been doing. And it's a culmination in the sense that all of the aspects of acid bases that we talked about figure into doing titration calculations. So you have to understand weak acid equilibria, you have to understand the relationship between Ka and Kb, between a hydronium ion concentration and hydroxide ion concentration. You have to be able to do ice tables, you have to be able to do the Henderson-Hasselbalch equation. So there are pretty much everything we have done in acid bases comes together simultaneously in titrations. So if you want to make sure that you have got the basics of acid bases down pat, titrations is the most comprehensive way to study all of that at the same time. If you find that you're having trouble with one particular aspect, yes, go do those specific types of problems so that you get your skill up in that. But if you want to see how you can do all of it in context, then titrations are a great place to do that. Question here. So do you just leave the carbonate alone? So if you wanted to know what happens to the carbonate, we would have to actually determine what the effects, what the quantitative effects on the bicarbonate and the hydronium ion would be. Here you're increasing both of them by the same amount, numerical amount, but they may not be starting at the same concentrations. So if you're starting already in an acidic solution, you may already have a bunch of hydronium, and so the sort of fractional change of hydronium would be smaller than the fractional change of the bicarbonate. And so then in that case, this is going to be a smaller arrow, this is going to be a bigger arrow, and you can say the carbonate is going to be increasing. But if instead you're in a situation where you already have a bunch of bicarbonate and you don't have much hydronium, then the argument would be the other way around. And so the reaction would be shifting the other way. So, when you have Le Chatelier having effects on both sides of an equilibrium, then you have to start thinking about the linear difference that you get here translating into fractional differences that you're going to have here. How do you, and if you wanted to know quantitatively how much it's going to change, then yes, you're going to have to do a sequential series of ice tables with different equilibrium constants. And Emily is saying that she's going to try to have some practice problems out soon. Excellent. Appreciate that. I also want to briefly mention, I've noticed in some of the Piazza questions that some people are still having a little bit of trouble knowing how to write down the equilibrium constant expression for an arbitrary reversible reaction. I put a spreadsheet up in the resources section of Blackboard that you can download, which will let you put in a random number into a box, and it will generate a random equilibrium equation for you to determine the equilibrium constant expression for. And if you then enter what that equilibrium constant expression is, and it'll tell you if you're right. And if you are stuck on it, you can click another box to have it display what the correct answer is. So it's relatively easy to use. So if that is a skill that you are struggling with, this thing can do, I believe, in the neighborhood of about 50 or 60,000 different equilibrium expressions that you can play with. So, all right. Thank you all, and we will be back to answering questions, either Muddiest Points or stuff in class tomorrow. There have been some requests to talk through some of the early questions on the small group activity, and I'm absolutely open to doing that if that is what people would like to do. In addition, I'm going to be thinking very hard over the next few days about what exactly the kinds of questions are that I want to put on the exams, and so I will while I'm not right now able to say there'll be a question like this, I will be trying to have a better sense of that coming up. Clearly, there's going to be some kind of buffer system that's going to be on there. And honestly, the buffer system that is in the small group activity is a very good kind of one to do. Obviously I'd want to pick a different system for you to be looking at. I'm thinking about going back to ocean water because ocean water buffers acid quite a bit because of CO2 that is in the atmosphere, and we have increases in CO2, and that's changing the pH of the oceans. And I think that would be an interesting thing to look at. And so there are some coupled equilibria and that are going on in that kind of situation. Okay, so that's it for today. Thank you very much.